Okay, everybody, going on to lesson number 2 here in the redox unit. All right, we talked about oxidation numbers. We talked about gaining and losing electrons, and how we can put that in a frame of oxidation and reduction. So oxidation is our loss of electrons. Reduction is our gain of electrons. So the one that's oxidized gives the electrons to the one that's reduced. Okay, and that completes the electronic transition. Okay, and then most chemical reactions take place with this electronic motion, with this movement of electrons from the one that's oxidized to the one that's reduced. Okay, or in that way. All right. So what we want to do in this particular one is take things apart a little, take the reaction apart, and actually track these electrons, see where they're going to and where they're coming from. So often when we want to do this, when we want to find how something works, what do? If we want to find out how a computer works, we take it apart. We look at the insides of it. We see how the mechanism runs. We see the power supply, the hard drive, the disk drive if there is one. We take a look at how everything is put together. We look at the fan. We look at the electronics on the inside. We look at the circuit board. If you want to find out how an engine works, what does a mechanic do? The mechanic takes apart the engine, looks at every little nut and bolt and piece. This way, when you put it back together, you know how it operates. So what we're going to do we're going to write something called half reactions. And simply what half reactions are is a way to take apart a reaction and examine where these electrons are going, where they're coming from, and where they're going to, and so we can see what happens. All right, so writing half reactions. So to find out how something works, we must often take it apart and view the insides. Okay, so writing half reactions allows us to see the electron flow in a redox reaction and then track it. And then the best part is to use this for something, and that's going to be important in a little while. Okay, so the first thing we want to do to write a half reaction, again, a half reaction is the oxidation or the reduction, is assign our oxidation numbers to all the elements in the reaction. Okay, so you have to be able to do that first. So assigning your oxidation numbers in the previous lesson. So you need to know how to do that. Then what we're going to do is identify the elements whose oxidation numbers have changed. We know that if you change your oxidation number, we change the electron flow, or we change the amount of electrons. For example, if you have an oxidation number of 0 in iron, and then you go to a +3, we know that change in oxidation number means I've lost 3 electrons. Okay. We're going to label oxidation or reduction, looking at whether that number goes up or down. Again, recall, if the number goes up, it's oxidation. If that number goes down, it's reduction. Okay. So then we're going to write half reactions by balancing by mass and electrons. Now, this is going to be the first time we've done balancing by electrons. We usually balance by mass by using coefficients, but we're going to balance the electrons too to make sure the charge is balanced. Because if you look up here, you'll see this charge is not balanced. We have one Fe and one Fe, but we have a 0 on this side and only a 3 plus on this side. So that's not good. That's not going to be balanced, so we need to fix that. And then we're going to add the reactions, and we're going to cancel the electrons. We're going to put it back together and form the regular reaction again. Okay, and again, the reason I'm doing this is I'm going to then provide myself with the correct coefficients to balance the equation. All right, so basically we're balancing by half reaction. So this is a different way of doing it, but again, nonetheless, the same idea. All right, so let's just say I have zinc and hydrochloric acid, and you could probably predict I'm going to create zinc chloride plus H2. So what I'm going to do is take this apart and take a look at where the electrons are moving. Now, historically, what we've done is we've said, okay, this is a single replacement, and fine, I'm getting zinc and hydrogen. Okay, but I want to assign my oxidation states first. So that's what I'm going to do. So I'm going to assign my oxidation states. Zinc alone is 0. We have to remember that. Hydrogen alone is 0. We're going to remember that. Okay, hydrogen is plus. It's an acid. It's +1. The chlorine is going to be -1. Okay, in this case, zinc will be +2. Chlorine is -1. If you have to slice and dice this, definitely do that. Okay, chlorine we know is -1. Times 2 is -2, so that means zinc has to be +2. So I have my oxidation numbers. So step 1, I go through my oxidation numbers, and then they are. So that takes care of step number 1. Okay, number 2 is I want to look across the arrow and look during the change which elements actually change. Okay, so let's look at the zinc for a minute. The zinc actually changes its oxidation number. It goes from 0 to +2. Okay, and chlorine goes from -1. Hydrogen goes from +1 to 0. So there's your two oxidation number changes. There's one changes here, one is the zinc, and one is the hydrogen. Now, the chlorine itself here does not change. The chlorine does not change. That's called a spectator ion. A spectator ion does not change. So we're not going to be concerned too much with the chlorine here. All right, so we're going to look at the first change is going to be an oxidation number. Why? Because what happens is the 0 becomes +2. So basically you're taking oxidation, the numbers going up, which is a loss of electrons. Okay. Now, a loss of electrons has to be matched with a gain of electrons. So in this case, the hydrogen will be reduction because the element is going from a 1 down to a 0, and that would be a gain of electrons. So the oxidation of zinc is the reduction of hydrogen. Now, what does that really mean? That simply means that oxidation, the zinc is losing electrons, and where are those electrons going? Those electrons are going from the zinc, and they're traveling to the hydrogen when they collide. All right, and there's be a transfer of electrons from one to the other. Okay, so let's just take a look at the anatomy of this. So we're going to write something called an oxidation half reaction. Okay, so what I'm going to do is I'm going to take my zinc out of here. Okay, just as you have the brackets, I'm going to take zinc 0. It's going to go to zinc 2 plus. So I'm basically going to pull it out of the equation. Okay, and what I'm going to do is realize that the 0 on this side, okay, and think about very maybe similar to what we did in nuclear where we balanced the atomic masses and we balanced the atomic numbers by putting numbers in here. But we're going to add negatives. We have to add electrons to one side or the other so that you balance the charge. Now, there's a 0 on this side, and there's a 2 plus on this side. So if I add 2 electrons to the right side, then this 2 minus here will add to the 2 plus, and I'll get 0 on the other side. So the 2 minus plus the 2 plus is equal to the 0 here. And now this oxidation half reaction is balanced. Okay, because I now have this reaction. So there's one zinc, my electrons are on the right. Now, if you think about this being a loss of electrons, and again, similar to the way we lose heat. When we lose heat, it's exothermic, and where do you put the heat in exothermic? You put it on the right. So when you lose electrons, they're always going to be on the right side. All right? Now, in a gain of electrons, in a reduction reaction, what we're going to simply do is put the same thing. We're going to take hydrogen. We're going to put hydrogen on the on the left side here, just like the hydrogen is on the left side of the arrow here. Okay, we're going to put an arrow, hydrogen 2. So again, anything in yellow here. All right, but what I'm going to have to do is, because there's 2 hydrogens here, we're going to have to put a 2 in front of the hydrogens here and balance it. All right, so hydrogen on this side, on the right, is going to have an oxidation number of 0. Now I'm going to have a 2 plus here, because I have 2 times plus. Okay, and the only way for me to make equal 0 if I add 2 electrons to the left. So down here is going to be your 2 minus. So your 2 minus here plus the 2 plus on this side is going to equal 0, almost like the reverse of what you did on top. All right? So a reduction has the electrons on the left, where an oxidation has on the right. Now again, this is the loss of electrons, and this is the gain of electrons. So basically, zinc is losing these 2 electrons, or becoming lost, and they're going and being gained on the right of this half reaction. So that's the electron flow. The electron flow is from the one that's oxidized to the one that's reduced. Think of this as like endoelectronic and this exoelectronic. You can think of it like that. All right, so then we're going to put a line. Okay, now we have the 2 separate half reactions, and now we're going to add them to a whole reaction. We're going to make a whole reaction of this. And the way we're going to do that is that because we are losing and gaining electrons, we're going to cancel those out. Those are lost and gained. They're on both sides of the reaction. I lose them and I gain them. All right, and I'm simply going to write what's left over. So here's my arrow. I have my arrow here. There's my arrow. Okay, and what's on the left side of the arrow? Well, there's a zinc 2 plus on the left side of an arrow. I'm sorry, a zinc 0 on the left side. Okay, and there's also a 2H plus on the left side. Again, here's the arrow. Here's the arrow. So on the left side of everything is that plus the 2H plus. Okay, and on the right side is my zinc 2 plus. Okay, and my H2 0. Okay, and this is called a net ionic equation. So basically what I did is I took this equation, the parent equation here. I took it apart and I put it back together, but I only put together the parts of the oxidation and reduction. I left out the chlorine. And the reason I'm leaving out the chlorine is the chlorine is not oxidized or reduced. Okay, so this is like a simplified version is the net ionic. All right, so we're going to add the half reactions by canceling electrons, and I end up with this parent reaction called the net ionic. Okay, so again, so final notes here. Spectator ion is a species which does not change their oxidation number. Okay, so it's not involved in the reaction, and again, your good example here would be chlorine minus. Okay, so chlorine minus is a spectator. All right, and a net ionic equation is the reaction written without the spectator ions. Okay, and that's how we're going to do this. So it's important to know why you're doing it. So again, this is how you write half reactions. Okay, and the best way to do it. All right, so basically to review, we're going to assign our oxidation numbers. Number one, we're going to identify those oxidation numbers who have changed. The zinc has changed, the hydrogen has changed. We're going to label them oxidation and reduction reactions, okay, in our reaction. And we're then going to write the half reaction. We're going to just take the ions, basically what you bracketed, you're just going to rewrite them. So zinc goes to zinc 2 plus. You're going to add your electrons into balance. Then you're going to write the reduction. You're going to do the same thing. You're going to add your reactions to balance. You're going to add those reactions by canceling the electrons. And you're going to get yourself a net ionic equation that is now balanced. Now, what do you mean by balanced here? Well, you're going to have a zinc and a zinc. You're going to have two H's and two H's. Now, we're also balanced by charge. Okay, we're also balanced by charge, which means balancing by electrons. So if you think about this, you have a 0 here plus a 2 plus on this side, which is 2 plus. And you have a 2 plus on this side plus a 0 here, which is also 2 plus on that side. So this is balanced all the way around. Okay, so let's just do some examples and check this out. All right, so let's add some reactions and balance in this kind of reaction. So I'm giving you just some isolated half reactions, and let's just see what we would do here. All right, so we got in the first example, number 1, we have iron 3 plus iron 0, or 2 goes to iron 0. How am I going to make this equal? Well, there's one iron and one iron, so we can leave that, that's fine. And this side is 0, so if I was to add electrons to the right side, if I was to add electrons here, that would be a mistake because 0 plus 3 minus is not equal to 3 plus. So that's not going to work. All right, so but if I add 3 electrons here, whoops, if I add 3 electrons to this side, I then can take the 3 minus plus the 3 plus and get 0. And because we're gaining electrons, this would be a reduction half. Okay? All right, in the next one, we have a 4 plus on this side and a 7 plus on this side. I would always try to balance by mass first. So if you have an Mn by itself, 1 Mn and 1 Mn is fine by mass. Okay, and the only way I'm going to be able to take a 7 plus and turn it into a 4 plus is if I subtract 3. So I'm going to have to subtract 3 from this side by adding 3 negatives. Okay, so again, that would be an increase in oxidation number. So I'd have to be oxidized. So I'd have to put electrons on the right, and this reaction would be an oxidation. This reaction would be a reduction. Okay, so again, 7 plus plus 3 minus is 4 plus. All right? All right, so in the next one, we'll see that oxygen is 0. It's going down to 2 minus. So that would be a reduction is gaining. Again, a reduction means electrons are going to be on the left. They're going into the system. Okay, but in this is a little different because I have 2 oxygens here, and I don't on the other side. So I'm going to have to put my 2 oxygens there. All right. What that does is that makes 4 minus here. So this is a 4 minus on this side, and I have a 0 on this side. So the only way to get 4 minus is to add 4 electrons to the left. And that's a reduction. So now that's charged. So 4 minus plus 0 is 4 minus. Okay? And 2 oxygens here is balanced by the 2 oxygens here. All right, same way on this side. We have 1 bromine and we have 1 bromine. Again, this is going to be a reduction. We have a bromine here and a bromine here. We need to put 2 bromines here. Okay, to have 2 more bromines there. And what do I have here is if I have a 10 plus here. I have a 10 plus here, and a 0 here. So that's really going down again, with reduction. So the only way I could do that is add 10 electrons to the left. Okay, and that will give me my reduction reaction. Okay, so you can see what I'm doing. I'm balancing by mass first, and then balancing by charge. Okay, so so that's a little practice in writing half reactions. Let's write a couple of half reactions to these guys. All right, so really quickly, I have manganese, and this is nice because I'm giving you the net balance equation. So let's say manganese is changing from Mn2 plus to Mn0, and aluminum is going from 0 to 3 plus. Okay, so let's look at the 0 to 3 plus. That's oxidation numbers going up, so that's oil, right? If your oxidation number is going up, so that's my oxidation reaction. If my charge is going from 2 plus down to 0, that means a reduction reaction. Again, reduction is gaining, my oxidation number is going down. So it really depends on what you want to write first. I tend to write my oxidation ones first. So my oxidation half reaction will be Al0 goes to Al3 plus. Okay. And the only way to get 0 on this side if I have plus is adding 3 electrons. Okay, so that would be 3 plus 3 minus is 0. And my reduction reaction is going to be Mn goes to Mn0. And the only way to get 0 on this side is to add my 2 electrons. Okay, now this is going to be a little interesting because what happens here, okay, is that the electrons lost here, 3 is not equal to the electrons gained. Not equal. So electrons lost must equal electrons gained. So what we're going to do in this case is we're going to multiply this reaction by a factor and multiply this reaction by a factor so that we get the electrons equal. So watch what I'm going to do. I'm going to multiply this reaction times 3 and this reaction times 2. And what that's going to do is equal to make 6 electrons on both sides. That makes life a lot easier for us. So watch what I'm going to do. I'm going to take everybody and multiply them by 3 here. 3, 3, and I'm going to make this a 6. And I'm going to take this 2, and I'm going to multiply this this by 2. My mistake. So this becomes a 2, this becomes a 2, this becomes a 6, right? And I'm going to multiply this by 3, this guy by 3, so that this becomes a 6, okay? This becomes a 3, and this becomes a 3, all right? So I'm adjusting the electrons so I get 6 electrons lost and 6 electrons gained. And now I can cancel them. And now I'm going to draw my line, okay? And now I'm going to write my new final reaction, my balanced reaction. Now what you can do is just simply take these coefficients and stick them back up in the equation. So if I have 2Al here, that's a 2Al here. If I have 2Al3 plus, I'm going to put 2Al3 plus up here. If I have 3Mn, I'm going to put 3Mn. If I have 3Mn0, I'm 3Mn0. Okay? So you could either rewrite it or you could just put the electrons back up in the top. All right? So that's a quick way you can do this. Again, you're going to have to use the factors that you need. All right? On this one down here, I'm not given the charges. I got to find them. Okay? We know Mg is 0. Silver is going to be 0 by itself. Don't forget things by themselves of 0. Okay? If I check this out or I look at the reference table, I'm going to find that oxygen's minus 2, nitrogen is plus 5 here, silver is plus 1. Okay, so plus 5. Okay, and again, the nitrate ion is really not changing here. All right, so I'm not going to really worry about it too much, but if we break this open, again, we'll find that oxygen is minus 2, nitrogen plus 5 again, and we know magnesium from the periodic table is plus 2. All right, so here's your things that are changing, right? We look at these numbers here, and we'll see that these numbers are the ones that are changing. Magnesium is going from 0 to plus 2, which is an oxidation, and silver is going from plus 1 to 0, down to 0, which is a reduction, And now we can write our half. So I'll write our oxidation half. We'll do this a little quicker. My oxidation is magnesium. So I'm going to go magnesium 0 is going to magnesium 2 plus 2 electrons. And the reduction reaction for this is going to be, again, you're just pulling out that. We're not going to worry about the nitrates because the nitrates are spectators. So we're going to take plus 1 to Ag0. The only way you're going to do that is if you add 1 electron, right? So it's 1 and minus 1 is 0. Okay, and again, we're going to look at the electrons and we're going to see here that the electrons are not equal. So the only way to make them equal is to take the reduction reaction and multiply that by 2. So we're going to take the 2, we're going to put 2 in front, 2 in front, 2 in front. That makes the electrons equal, so I can balance them out. And now I could take my 2 Ag plus, place that back up in the reaction, take my 2 Ag, put it back up in here. Okay, I might have to adjust a couple of things, but it looks pretty good. All right, and it looks good. So again, 1, 2, 2, and 1 would be the reaction. If you wanted the net ionic, you would add these together and cancel the electrons. So I would get my net ionic equation would be Mg0, right? Mg. What else is on the left side? Oh, I shouldn't have crossed that out. This has to be here. So Mg and then plus 2 Ag plus, right? Arrow, again, you're going to use the 2 arrows here, and whatever's left over on the right, which would be Mg plus 2 plus my 2 Ag plus. Okay. So again, notice that these coefficients here are the same coefficients up in the parent reaction, except that you're removing the spectator. Okay, and again, NO3 minus, okay, is equal to your spectator. All right? So that's the important thing. Those are 2 good examples. If you need to go back over them and check them, review them, and definitely practice the ones that are in your packet on the next pages, because those will be very good ways to get this under your belt. All right, have a great day, guys.